All right. Yeah, I think you've probably all seen, or most of you have seen this keyboard before. I will begin by playing a song. Tube amp, so a little fiddly with the noise. Um, so um, this talk is what this is. This is a microtonal keyboard. Uh, the has a bunch of pressure sensitive keys, a set of knobs up in the upper left that control sound parameters like volume, reverb level, and so on. There's a menu system in the middle. It uses a Teensy 4.0 microcontroller for that's sort of the brains of the whole thing. It has an audio out. There is a local synthesizer that's playing on the keyboard that is in this case being sent out to this PV2 amp. Has MIDI in and out, USB MIDI as well. It also has CAN bus, which I kind of added on a whim. And at the bottom, there's some control buttons for things like transposing and doing pitch bend and whatnot. Uh, let's see. So basically, the structure of the talk is that I answer a bunch of, answer the questions that I usually get, like, why did you make this thing? Why does it look like that? How does it work? How did you build it? So to begin with, the kind of strange explanation of why I built it was that the 12 through the 2 to the fourth power is kind of a fairly lousy approximation of 1 1/4, which, you know, might not make a whole lot of sense. So I'll have to explain that a little bit. So in most modern music, we use a 12-tone equal tempered scale, where you take an octave, which is a doubling of frequency, divided up into 12 logarithmically equal steps so that each note is basically the frequency of its neighbor multiplied or divided by the 12 through to 2. And so if you take, say, 4 steps of that, that's the 12 through to the fourth power, and you get kind of close to 1.25, but not really that close. So here's a difference between, on the bottom we have the standard equal tempered scale that we usually use, and mapped out logarithmically, so everything's spaced evenly. And then above it, we have a bunch of numeric ratios that those numbers approximate. So there's this question: why do we use 12 tone equal temperament and not 11 tone equal temperament or 13 tone equal temperament? Well, there's kind of a non-obvious answer to that, which is that if you pick a whole bunch of really small number ratios, then the 12 tone equal temperament matches up pretty well. Like you can see that, like, oh, 3/1.5 is very close to the G right here, only off by interval of 2 cents. Same for the perfect fifth, perfect fourth. Some of these, there's a bit of a significant discrepancy, like that 5/4 there doesn't match up with an E. Quite right. It's close, but it's not exactly dead on. And by the way, cents are a tuning system unit. A one equal tempered semitone is 100 cents. So 13 cents is about a seventh of a semitone. And you can actually hear this. It's not that subtle. I can give an example here real quickly. Okay, settings, tuning. I just implemented this feature last night that I can play a chord, and then I can turn pitch quantization on, so I can quantize it to the 12 tone equal temperament. This is the same chord in equal temperament. And here is the exactly tuned version again. And it gets even more extreme if I use intervals that don't even have a close approximation. Like if I'm doing a dominant seventh chord, here's the equal tempered dominant seventh. And then here's the exactly tuned dominant seventh. Yeah, it's not a subtle difference. It's pretty noticeable. So why do we use 12 tone equal temperament in the first place? So basically, it's because it's very convenient. You can pick any note as the root of your key, and it doesn't really matter. It's very easy to build instruments because you only have to deal with 12 pitch classes, and everyone agrees on what notes all the instruments have. And there's not really any hard questions like, hey, should this instrument have a D flat on it or not? Everyone's just kind of all agreed that yes, it should. Where, on the other hand, if you tune to the exact ratios, and that's a system called just intonation, by the way. It just kind of sounds better. Everything's in tune. You don't have the beat frequencies that we perceive as out of tuneness. So it's a trade-off that you can make, but not very many instruments do this. And so what happens if you actually decide you want to do exact tuning? Um, well, one of the things that you come across is that, oh, it turns out I need more than 12 notes per octave, even to play music that was originally notated for 12 notes per octave. Like that Bach piece that I played early, I'm using 15 different pitch classes to play that song. Um, Even though it wasn't intended to be played on a 16 tone or a 15 tone instrument. It was meant to be played on a 12 tone instrument. Um, and if you go to the do the just intonation approach, you get a lot of chords that are kind of uh, if you it, there's some very subtle distinctions in note, and you have to have these notes that are close, but not quite the same. Like on this graph, the 10/9 and 9/8, 12 tone equal temperament just kind of treats those as both the same, um, and you don't have to worry about that distinction. But if you do start having to care, because if you play the wrong one, the chord sounds out of tune, then you end up with more notes. Um, somewhere around 16 is probably a reasonable minimum for playing, ordinary Western music that doesn't change key very much. Um, yeah, I think so. And so here's a reasonable 16 tone scale. And this is laid out using a diagram called a lattice, or it's also called a tonnettes. And basically the idea is you laid out all the notes of your scale on a grid. And if you're moving, um, the horizontal axis in this grid is moving in perfect fifths. So, in the middle you've got C, and then a fifth up from that is G, and a fifth up from that is D. The up and to the right, those diagonals are moving by powers of 5. Um, and so the up and to the right is an interval of a major third, and down and to the right is an interval of a minor third, which is a 6/5 ratio. And there's some interesting things about, I mean, these are very useful diagrams for looking at chords, because you can see, oh, the C major chord, which is right there, you can tell, oh, it shares 2 notes with, E minor, which is just above and to the right of it. Makes it kind of easier to understand chord transitions. So they're kind of handy. But I mean, you'll also notice that there's there's a D here, and then there's a D over there, and they're slightly different Ds. They're not the same in just intonation. In equal temperament, this grid would just kind of go off to infinity, and you just repeat the same notes over and over. But in just intonation, this grid kind of goes out to infinity and never repeats. And those are all valid notes. And so you have to kind of decide, when you're making an instrument, how far do you want your lattice to extend. Uh, and it's kind of interesting, the numerical interpretation of the different axes of the grids are based on prime numbers. So the horizontal axis, you're dealing in factors of 3, and the other axis, you're dealing in factors of 5. You could make this, each time you add a new prime number, you add a new axis. So if we add factors of 7, this starts getting kind of hard to look at and understand, because you're flattening a 3-dimensional structure down into a two-dimensional space. So there's this problem of, how do we make a keyboard layout out of this? The standard piano Halberstadt layout doesn't really work that well because that's designed around 12 notes. Um, Grid layouts are space efficient, and that's sort of what most people do for doing interesting microtonal controllers. Is they use a regular square grid or hexagon grid. I didn't do that because I kind of have this weird eclectic collection of notes that didn't really fit very well into a regular grid. So um, uh, basically the previous diagram showed just kind of one octave. If you have multiple octaves, then you get, 4 octaves. You're basically duplicating it 4 times, and it gets even more chaotic because now you've got a 4-dimensional grid that you're mashing down into 2 dimensions. But if you rotate that around enough and then you run a Voronoi diagram solver over it once you found some rotation where none of the notes are crowding each other too badly, you can get an interesting, an interesting keyboard layout that actually works, and it's isomorphic. So, a major triad is the same shape wherever you are on the keyboard, which makes it easy to learn relatively. Uh, and if you want to know how to navigate this, here's what a major scale looks like. Um, the yellows are the major third and the major sixth and seventh. And if you substitute the blue notes right below those yellow notes, you get a minor scale. So fairly intuitive. Um, so that's about as much as I want to talk about the keyboard layout. I could talk for a long time, but uh, to get on to the rest of the talk of the other big question is, how in the world does this whole thing work? So the keyboard, it's powered by a Teensy 4 that kind of runs the whole thing. There's kind of an unusual multiplexer setup that allows me to scan the keys. I'll talk more about the keys in a moment. It also runs. There's a kind of a basic user interface, um, and this thing either can spit out either MIDI, which this is the way I used it for a long time. Is that uh, you'd plug this thing into an external MIDI synthesizer, some kind of sound engine, something with the capabilities to understand the MIDI that it emits, because MIDI was never really designed around the microtonal use cases. It was kind of designed around piano use cases. But there's some cool things you can do to make that work, and MP standard makes that a lot easier. Um, there's also, I added a DAC to the DAC and a headphone or a line out to the printed circuit board a long time ago, and just about 6 months ago, I got around to actually adding an audio synthesizer. So you don't actually have to plug it into a laptop or some external synthesizer. You can just plug in headphones and use it as is. Let's see. Um, as for the keys, if you look very closely, so the keys are they use force sensitive resistors. If you look very closely at the keys, I'm using kind of a interdigitized fingers approach, where you have uh, you know exposed gold-plated copper traces that um, they do that. And if you lay a force-sensitive resistor over the top, which is just a material that has a certain electrical conductivity that changes as you press on it, it turns into a variable resistor. So by measuring how many ohms that resistor is, you can infer what the key pressure is. Um, I use a very kind of a unusual approach for multiplexing these. The standard thing would be to just use ordinary multiplexers. I didn't do that for, um, honestly, I don't remember why, but uh, what I'm doing here is I'm using shift registers, and I'm using an unusual kind of shift register. It's a high power shift register with open collector outputs. And what that means is that, normally a shift register, it's when the output is on, it's emitting the supply voltage, which is in this case, either 3.3 or 5 volts. But if it's off, it's emitting 0 volts. Well, the open collector shift register is different. When it's on, it's a low impedance path to ground, and if it's off, it's high impedance. It's like it's not connected at all. And so what I do is I basically connect the grounds of all these key sensors to shift register outputs, and only one output is on at a time, which means that only that one key is connected to ground. And so there's a pull-up resistor that's shared by all of these keys, but only one key is the path to ground, so that's the one that you're reading. And the microcontroller uses one of the analog to digital converter input pins to read the analog voltage at that pin. And this whole setup is replicated 4 times. I've got four um, 4 rows of shift registers, and it basically means that I've built a 160 channel digital ohm meter. That's sort of the way to think of it. And I am able to scan that about 500 times a second, which is good enough for musical applications. Oh, one of the advantages of doing the shift register approach um, is that over the multiplexer setup is that if you're using multiplexers, it's basically a digital switch that has a number of address pins that decide which output you're listening to. Um, the with multiplexers, the number of inputs is limited by the number of address pins. And this shift register approach has this interesting characteristic of that you can just attach more things off the end of your shift register bus, and you can basically go on forever adding more stuff, and you didn't have to change anything. Now, eventually, you'll run into electrical signal integrity issues if you try to read 10,000 inputs instead of 40 or whatever per shift register row. Um, but it makes it very versatile. And I've actually added a little expansion port that I've never used to the Mosaichord that you could in theory plug another. You could daisy chain a bunch of key beds onto the same Mosaichord. There's reasons why that might not work very well in practice, but it's a thing that could be done. Uh, so the firmware, it's ordinary C++ code. I use the Arduino IDE. The firmware is all open source. You can find it on GitHub. Uh, and the firmware is basically it runs an event loop that does most of the things that you'd expect, like scans the key bed and turns key pressure into the appropriate MIDI signals, and it runs the audio synthesizer. Uh, has a very fairly rudimentary user interface. But one of the things I did just fairly recently was that's kind of not related to anything else in this talk, but I wanted to mention it because it was kind of fun. Was that I ended up writing a font engine and defining my own typeface, which is actually kind of fun. Um, and so here's the main thing I wanted from my font engine was to be able to um, write, um, make symbols, make new characters just from from the C++ code editor. And so here's a flat symbol, um, and it's basically just I'm sending a bunch of bytes in binary format into the constructor of one of these character glyphs, and using the C++ binary format, you can arrange this thing into rows that match up with pixels, so you can literally put ones where you want your pixels to be dark. So the section on the left is all the um, full brightness pixels and the off pixels, and then the section on the right um, is the I decided to implement some degree of anti-aliasing, so those are the half-on pixels to make the corners look sharper and less jagged. Um, yeah, so that was a fun little digression. Um, I I'll, just for the sake of brevity, I probably won't. I guess I won't go into the how the microtonal MIDI part works. Um, Um, the internal audio synthesizer is using I use the Teensy Audio library for most of the heavy lifting, and I did the simple thing, which is to implement a subtractive synthesizer, which is kind of mimics what an analog synthesizer would do, where you start with basic waveforms like sawtooth and square, triangle, sine wave, and then you run that into a resonant low pass filter. And key pressure modulates the volume in filter cutoff. So um, physically, how this thing goes together, the wood parts are made out of birch ply, that are dyed with transient dye, and there's felt glued to the back of the keys to give them a little bit of a squishy feel, because it's kind of weird to be pressing on something that's rock hard, solid. Uh, the PCBs were designed in KiCad. I had JLC PCB do the manufacturing and assembly. There's still some surface mount stuff that I solder myself, but most of the hard stuff is done with a pick and place machine in a factory. Um, and the force sensitive resistor material I'm using is Velostat. Uh, it's an interesting material. It's pretty cheap, and it seems to perform really well. There's the physical stack up of how this goes. I've changed how the most recent ones have a little cover that goes over the microcontroller and some other cosmetic changes, but mostly this is how they all go together. Oh, and here is looking back, this is the original version that I made. People who have come to Dorkbot for a long time or uh, longtime members of this makerspace might recognize this thing. Um, it didn't work that well, but it worked well enough to prove the concept. Um, and something that's kind of useful to think about is if I had tried to do this project 30 years ago, 20 years ago, how hard would it have been? And it would have been a lot harder because a lot of things have just gotten easier about making stuff. These days, pretty much anybody can make a PCB if they kind of know generally how electricity works, and they're willing to learn how to use KiCad. The manufacturing is really surprisingly cheap, even in tiny volumes. Laser cutters have gotten really cheap, which is another thing that made the manufacturing the parts possible. Teensy 4 and the software ecosystem made this um, a lot easier. Um, I didn't talk at all about using Haskell in this project, but that's that's what I wrote, the tool that generates the keyboard layout. The MPE standard, that being around, the fact that Roger Linn and the Linstrument existed before this came along made that part of it easier because people are now actually caring about making expressive controllers and things that respond to key pressure. And a neat thing that kind of snuck in the back door with MPE is that if you have MPE, it's really easy to do microtonal stuff as well as just expressive music. Surge XT, the synthesizer, made life easier for uh, before I had the internal synthesizer, I needed something to easily demo, and being able to just run Surge on a laptop made that a lot easier. And it's also great that Surge is around for people who are doing interesting synthesizers because they don't have to build a sound engine into their product. Uh, they can say, oh, use this open source um, synthesizer that has a bunch of patches already that are optimized for expressive controllers. Uh, and it's a nice, easy uh, uh, end user experience that you don't have to go out and buy, a $500 piece of software or whatever to use the thing. Uh, and that's it for my talk. Any questions?
What I was thinking of earlier when you were talking about the boxies, I was curious if those kind of extra notes you needed in the scale, is it because of like parts where it gets chromatic, or like you have chords that are a little outside the scale and you have to like compensate for that, or like having a different root note? Is that kind of what that stems out of? Or do you, and I guess the related question was whether you have to uh, like basically adjust the entire scale of the instrument to play in a different key, or does it just have all the notes for the different keys?
Yeah, so questions are, what drives the need for all these extra notes, and can you use does it have all the notes you need for all the keys, or do you need to change key? So the latter one's the easier question. So that's it's you know it has most of the notes that you would need for a particular key, and if you want a different key, you'd have to transpose the whole keyboard, and there's an interface for transposing. You can choose the root to be whatever you want. Um,
relate back to that root note, it makes sense that you would have to.
Yeah. It's like the 1/1, whatever your root note is. I mean, the default I set is C, but if you want it to be D, it can be D or anything else you want. The question about needing additional notes is that one's kind of interesting. So imagine you're in the key of C major and you want to play all your chords, and you have let's see, you have say C major. Traditionally, you need 7 notes. You need that one, that one, that one, that one, that one, that one, and that one. And what happens if you want to play D minor? Well, there's a D minor over here, but you need that 10/9, which wasn't in your scale, to play that note. I mean, you could play 9/8 instead of 10/9, but you're using notes that aren't really related, and it sounds awful. The other, let's see, there's another. I think it's this. Yeah, it's this one over here. It's not labeled, but there's another D minor over there that's just slightly down for it's or actually it's a like 22 cents sharp of that one over there. But if this uses the D that you already have in the major scale, but you'd need this 27/16 and 27/24 or 27/20. And so it's like, oh, just to play the basic chords of C major, you need 8 notes all of a sudden instead of 7. And that happens in a number of other places. And pretty soon you realize, oh, to play chromatically, you need like, a bunch of these extra notes. Okay, your question? Do I know anyone who can play it better than me? Yes. There's one that's sitting right behind you, Timmy over there.
Also, have you put time into learning it or just
Yeah, I've put some time into learning it. I'm not an amazing musician myself, and I don't really aspire to be, but I enjoy playing music in my, I usually don't play publicly. This is like one of 2 public performances I've done on this keyboard. The other one went rather badly. But yeah, I don't really have a good memory for remembering songs, so it's kind of laborious to learn things. And I had the additional constraint that for giving talks like this, I wanted something that was very definitely in the public domain, so that the YouTube video wouldn't get taken down. So it's like, oh yeah, I guess I'm learning Bach then. Yeah.
So, the types of temperament that are being used popularly change over time. Like, I think they did well tempered,
Yeah.
tempered in box time. So, just the microtonal layout, like, are you able to approximate that in about the same way you do 12
Okay, so the question is, does this microtonal layout approximate some of the historical temperaments like mean tone? Yeah, I mean, it gets into the finer details of how the compromises people made with the historical tunings. In a way, just intonation is the oldest tuning system, because just tuning directly to whole number ratios is what you would just do if you were, if you have 2 strings and you're tuning them to each other. Those are the intervals that sound good, so that's what you'd pick. And then the mean tone and well temperaments and Workmeister and all the other various approaches before equal temperament came up were just ways of kind of shoehorning a bunch of notes into a 12-note scale and making the compromises not too bad. And so those temperaments sounded different than 12-tone equal temperament because they made different compromises. Timmy.
Can I play a tune?
Yes, sure.
Oh, yeah.
Yeah. Do you, is it set to your liking?
Yeah, it's good.
Okay. Well, I forgot to mention that we've got a setup over at the Winter Light Festival. So we're set up over at the me and Timmy have an installation over at the Electric Blocks, which is a couple blocks northeast of OMSI. We've got these keyboards set up, some another microtonal instrument, and a giant strobe tuner that's definitely worth seeing.
I haven't been out there yet, but now I know that I need to.
Yes.
When can I go there? Anytime at all?
Friday and Saturday, 6 to 10 p.m. is when most of the stuff. There might be some other stuff that's open all week. I'm not sure, but yeah, the we were set up last weekend, but there's one weekend more. All right. I guess that's all.